Okay, so this example is equilibrium of a particle in 3 dimensions. So we have a flower pot with a mass of 40 kilograms, and it's all in place by 3 cables. So the first steps will be to make the free body diagram. We will use the particle A. We have the weight that is going down, and 40 times 9.81 is 392.4. Okay, let's see the axes. So we have ax. Oops, I want to make them in gray. Ax, the y, and the z. W is aligned with the z axis. The tension that we don't know, there is TAC, aligned with hi-hat with ax, TAB, aligned with the y, and TAD is going somewhere on the back, something like that. So now the second steps will be to write, oops, what I did. Write the forces in Cartesian notation form. Cartesian notation form. Okay, so we have W that is on Z, so minus 392.4 on K hat. We have the tension TAC, oops, TAC, that is on I hat only, so TAC magnitude time direction I hat. We have TAB, that is equal to the magnitude of TAB, and it's aligned with J hat. And after that, we need to find TAD. So remember, we need to find the vector position, the unit vector, and at the end, we can have the TAD. So let's find first the RAD, vector position. Okay, so we go from A to D. First on I hat, we are going minus 1.5 on I hat. On J hat, we are going minus 2 on J hat. And on Z, we are going up, so plus 1.5 on K hat. So that's the vector RAD. The magnitude of RAD is the square root of 1.5 square plus 2 square plus 1.5 square. That's the square root of 8.5. So we can write the unit vector UAD. That is the magnitude, that is the vector RAD divided by the magnitude for each component. So we have minus 1.5 divided by the square root of 8.5 on I hat, minus 2 divided by the square root of 8.5 on J hat, plus 1.5 divided by square root of 8.5 on K hat. That's for the unit vector. So now that we find the unit vector direction, we can write TAD in terms of the magnitude of the unit vector. So minus 1.5 divided by square root of 8.5 TAD on I hat, minus 2 divided by the square root of 8.5 TAD on J hat, and plus 1.5 divided by the square root of 8.5 on K hat. Here we go. So now we have all the vector. We have W, we have TAC, we have TAB, and we have TAD, this huge one. Okay. Oops. We have 3 unknowns: the magnitude of TAC, the magnitude of TAB, and the magnitude of TAD. Oops, I forget TAD on this one. TAD, right? But that's the same. So that's 3 unknowns. So we only need 3 equations, and we are on a particle, so we can solve only for 3 equations. So that's perfect. If we look closer to the equation, TAD is the only force that has a force on K. Okay, so maybe we should use this one first, this equation first. So we will use, oops, let me move this there, third equation of equilibrium. Oops. And the first equation that we will use is sum of the forces on Z equals 0. because what we have on Z, if we look at the free body diagram, we have W, so minus 392.4, and we have this complement for TAD plus 1.5 divided by the square root of 8.5 for TAD, and it's equal to 0. And we can solve for TAD. So we got TAD, that is 392.4 times the square root of 8.5 and divided by 1.5. This is 763 Newton. That's for TAD. Oops. One tension. And after that, we are lucky. We can use TAC on J hat or TAB. So it doesn't matter now. Sum of the forces on X is equal to 0. What do we have on X? We have TAC, that is on the positive I hat, and minus 1.5 divided by the square root of 8.5 times TAD equals 0. So we got TAC, that is equal to 1.5 divided by the square root of 8.5. And TAD is 7763 Newton. So we got TAC, it's equal to, so this one, times 1.5 and divided by the square root of 8.5. 392.4. We come back on our weight. Okay, so that was for the force on X, and let's do in purple the last one. We will use now J hat. So sum of the forces on Y equals 0, and we got TAB, and minus 2 divided by the square root of 8.5 times TAD that we found before equals 0, and we'll replace again TAD by 763, and we got TAB that is equal to 2 times 763 and divided by the square root of 8.5. That's 523 Newton. And I should write this one 392 Newton, just to keep three significant number. Oops, let's me square TAC and let's me square TAB. So we were able to solve for each unknown we were able to have one equation of equilibrium to solve for one unknown at a time, okay? But we need to look at the equations and we need to begin by sum of the forces on Z equals 0. That's the first steps, because that's where we have an information. We have W, the value of W, and second, we just have TAD that has a complement on K, on Z, on K hat on Z. So that's it. It's a short, sweet problem. Just be careful to not make mistake at the beginning, because it will show on all your answers after that. See you in the next video. Bye bye.